Lewis and Clark Lake, situated on the border between Nebraska and South Dakota, might not remain a lake for much longer. This vital reservoir, along with its dam, provides essential hydropower, critical flood control, and underpins a thriving recreational economy that supports fishing, boating, camping, birdwatching, hunting, swimming, and biking. Yet, all these benefits face an existential threat from a seemingly innocuous menace: dirt. Approximately 5 million metric tons of sediment flow down this section of the Missouri River annually, settling into the lake. Since the dam's construction in the 1950s, this constant influx of sand and silt has formed a massive delta at the river's entry point. The reservoir has already lost about 30% of its storage capacity, with one study projecting it will be half filled with sediment by 2045. What if a seemingly simple problem, like dirt, could lead to a global catastrophe, threatening vital infrastructure and baffling engineers with its complex solutions? You might be surprised by the answers. The impacts of dams on sediment movement are felt on both sides. Downstream, these impacts are primarily environmental. We instinctively think of rivers as carriers of water, a definition that seems straightforward. However, anyone who has witnessed a river turn the color of chocolate milk after a storm knows they are also powerful transporters of sediment. The natural flow of this sediment plays crucial roles within a river system. It distributes nutrients throughout the watershed, forms vital habitats and riverbeds for fish, amphibians, mammals, reptiles, birds, and numerous invertebrates. Furthermore, it fertilizes floodplains, stabilizes riverbanks, and contributes to the formation of coastal deltas and beaches that provide essential buffering against waves and storms. Depriving a river of its natural sediment supply can profoundly alter the entire ecosystem downstream from a dam. Just as a river is more than a mere water carrier, a reservoir is far more than a simple water collector. To illustrate this complex process, a model has been constructed. This is an acrylic flume. It has been tilted to create two distinct types of flow. On the right, a fast-moving stream simulates a river, while on the left, a small dam has been constructed using stop logs. These logs raise the water level, slowing its flow to a gentle crawl. Mica powder has been added to the water to clearly visualize the difference in velocity. Now, let's introduce some sediment. Bags of colored sand will be dumped into the sump, where the pump recirculates water through the flume. Observe what unfolds in the time-lapse. The river's swift current carries the sand downstream, but upon entering the reservoir's slower flow, the sediment begins to fall out of suspension. Initially, this is a somewhat chaotic process, with sand dispersing widely. However, a delta gradually begins to form precisely where the river converges with the reservoir. As the river flows over this developing delta, its speed naturally increases, causing subsequent batches of sediment to deposit further downstream. Each addition of sand to the pump progressively contributes to this accumulation, as the mass of sediment steadily fills the reservoir, advancing towards the dam. While this visual demonstration is compelling, it's crucial to understand that the process it illustrates is highly problematic. Although some dams are deliberately designed to retain sediment, in the vast majority of cases, this accumulation is an undesired consequence of impounding water within a river valley. The primary purpose of most reservoirs is water storage for flood control, electricity generation, drinking water supply, irrigation, and cooling power plants, among other uses. Consequently, as sediment progressively displaces more of the reservoir's volume, the overall value it provides diminishes. This leads to several additional issues. Shallower reservoirs restrict recreational activities by reducing navigable areas and promoting undesirable algal blooms. Silt and sand can also clog the dam's gates and outlets, damaging critical equipment like turbines. Furthermore, sediment can exert unanticipated forces on a dam, complicating its structural design. Dirt is denser than water, compounding the already challenging task of constructing massive structures capable of retaining vast quantities of water. Perhaps the greatest challenge of this problem is its inherent inevitability. No natural river or stream exists without carrying some amount of sediment. While the magnitude varies geographically, across the globe, we have constructed numerous dams. Many factors influence how rapidly sedimentation becomes a critical issue in a reservoir, primarily those affecting water-driven erosion in upstream areas. Soil type is a significant factor. Sandy soils, for instance, erode more quickly than silts and clays, hence the choice of sand for the model. Land use is another crucial element. Vegetated regions like forests and grasslands retain their soil more effectively than agricultural land or areas impacted by wildfires. Yet, in almost all scenarios, without proactive intervention, every reservoir is destined to eventually fill with sediment. Naturally, this is a detrimental outcome, yet the full extent of its severity is often underestimated outside a small community of industry professionals and environmental advocates. Dams represent some of the most capital-intensive projects undertaken by humanity, often involving billions of dollars for individual constructions. Generally speaking, society frequently accepts substantial downsides in addition to these immense monetary costs, such as environmental impacts and the risk of downstream failure to people and property, in exchange for the immense benefits dams offer. Sedimentation is a problem that unfolds over decades, making it easy at a project's inception to defer the solution to future generations. With a peak era of dam construction occurring roughly from the 1930s to the 1970s, we are now confronting this challenge, paradoxically, at a time when we are more dependent on these dams than ever before. Unfortunately, there are no simple solutions. To some extent, sediment accumulation is accounted for during the design phase. Modern dams are engineered to tolerate these forces, and reservoirs typically include a dead pool, a specific volume initially reserved for sediment accumulation. Low-level gates are positioned above this dead pool to prevent clogging. However, this is less a permanent solution and more a temporary accommodation, as even this designated dead pool will eventually fill. For many, the most straightforward solution seems to be simply removing the dirt from the lake. Dredging soil is a technique humanity has employed for millennia, and in certain situations, it remains the only viable option. Methods range from using excavators on barges or cranes with clamshell buckets to suction dredgers that operate like giant vacuum cleaners, pumping sediment slurry to barges or shore. However, the term feasible is critical here. The efficiency of dam construction lies in moving and placing a relatively small amount of material to create a vast storage capacity. Depending on the topography and design, a single cubic meter of earth or concrete used in the dam itself can yield hundreds or even tens of thousands of times that volume in reservoir storage. In contrast, dredging is a one-to-one process. For every cubic meter of storage you wish to reclaim, you must physically remove a cubic meter of sediment from the reservoir. At this scale, the costs often far outweigh the benefits. There's a fundamental reason we typically don't excavate enormous holes solely to store large volumes of water, and that primary reason is cost. The 5 million metric tons of sediment annually flowing into Lewis and Clark Reservoir would fill approximately 200,000 end-dump semi-trailers each year, assuming the sediment is dried first, which, incidentally, presents another significant challenge. The dredged material, or spoils, are not like regular soil. Firstly, these spoils are saturated with water, which significantly increases their volume, necessitating the hauling or disposal of more material. This moisture also makes the spoils challenging to handle and transport. Various methods exist to dry or dewater them, as professionals term it. A common technique involves pumping the spoils into geotubes, large fabric bags that retain the solid material while allowing water to slowly drain out. This, however, adds another layer of complexity and cost. Secondly, sediments can sometimes be contaminated with pollutants washed from upstream land. Such cases demand specialized handling and disposal procedures. Given that many countries enforce stringent environmental regulations concerning dredging and spoil disposal, it becomes clear that dredging is rarely a simple or cost-effective solution for reservoir sedimentation. Another strategy for managing sediment is to allow it to pass through the dam. This approach is often considered ideal because, as previously discussed, sediment fulfills numerous vital functions within a river system. Enabling its continued journey downstream effectively addresses two problems simultaneously. There are several methods to achieve this. Some dams feature low-level outlets that continuously release turbid water reaching the structure. However, recalling the model, not all sediment reaches the dam. In most instances, the majority of sediment deposits furthest from the dam, and much of it only approaches the dam once the reservoir is nearly full. Naturally, the model provides a simplified, two-dimensional representation with a single soil type. As with all sediment transport phenomena, conditions are constantly evolving. Indeed, observing the model running in time-lapse reveals the dynamic nature of this process. Nevertheless, in most real-world scenarios, a significant portion of the sediment deposited in a reservoir tends to remain in place or takes many years to eventually reach the dam. Consequently, another alternative is reservoir flushing. This involves opening the dam gates wide to generate water velocities sufficient to loosen and scour accumulated sediment, resuspending it for downstream transport. This technique was attempted in the model and yielded promising results. However, this remains a two-dimensional representation. In a real reservoir, which possesses significant width, flushing typically only carves a narrow channel, leaving the majority of sediment undisturbed. Inevitably, this process necessitates drawing down the reservoir, effectively sacrificing a substantial volume of stored water. More critically, it releases a massive plume of sediment-laden water downstream. While the importance of sediment downstream of dams has been emphasized, and it is indeed its natural place, excessive release can be detrimental. Sediment can be classified as a pollutant, and is, in fact, regulated as such in many regions, including the United States, which explains the use of silt fences around construction sites. Therefore, the challenge of releasing sediment from a dam lies in precisely matching its rate and quantity to what would naturally occur if the dam were absent. This is an exceptionally difficult task due to the inherent variability of natural sediment flows, the altered dynamics of sediment transport within a reservoir compared to a free-flowing river, the operational constraints imposed, such as the need for reservoir drawdown, and the complex regulatory framework governing sediment releases into natural waterways. The third primary approach to addressing this issue is to reduce the amount of sediment that reaches the reservoir initially. Innovations exist for capturing sediment upstream, such as bedload interceptors positioned in streams to gradually remove material. One could also employ a fight fire with fire strategy by constructing check dams to trap sediment, though this effectively solves reservoir sedimentation by creating new, smaller reservoirs of sediment. As noted, sediment loads are heavily influenced not only by soil types within the watershed, but also by land use and cover. Soil conservation is a vast discipline that has significantly shaped land management in the U.S. since the Dust Bowl of the 1930s. There is an entire government agency dedicated to this problem, along with a wide range of erosion reduction strategies, and many other nations possess similar resources. These strategies often involve maintaining robust vegetation, preventing wildfires, implementing sound agricultural practices, and reforestation. However, the sheer scale must be considered. Watersheds for major reservoirs can be immense. Lewis and Clark Reservoir's catchment, for example, spans approximately 41,000 square kilometers, an area larger than the entire state of Maryland. Managing such a vast area is an inherently complex undertaking, particularly given the long-term commitment required. Consequently, in many situations, there's a limit to how much sediment can realistically be kept at bay. This, however, is merely an overview. While Lewis and Clark Reservoir serves as a compelling example, this problem extends to virtually every on-channel reservoir worldwide. The expansive nature of the issue has spurred the development of a vast array of solutions, which could easily fill hours of discussion. This is, in itself, encouraging. Though most solutions are far from simple, it doesn't preclude the possibility of developing long-term sustainable infrastructure. The engineering lessons gleaned from past oversights have equipped us with numerous new tools to optimize the use of our existing infrastructure moving forward. Understanding and addressing these challenges is crucial for the future of sustainable water management globally.